Welcome back to Probability and Statistics 1. This is Unit 1, Introducing Probability, the Mathematics of Uncertainty. In this unit, we're going to introduce the basic concepts of probability. We'll talk about the axioms of probability theory, and we'll deduce some elementary consequences of those axioms that'll sort of set the stage for the rest of the work we do this semester. The basic setting for probability theory is this idea that we encounter sometimes processes that have a set of possible outcomes, but you can't predict beforehand which outcome is actually going to occur with certainty. A process like that is called a random process, and that's the basic object of study in probability theory. You can think of a lot of processes like that, right? Like toss a coin. Could be heads, could be tails. Roll a pair of dice. You might get a sum of 7, you might get a sum of 11, you might get something else, right? Physical processes are often describable in this way. The Earth's climate, for instance. We could think about what's the average temperature on planet Earth going to be in 25 years, and there's a range of possible outcomes, and some are going to be more probable than others. So probability is all about quantifying that uncertainty in the prediction of the outcome of a random process. Some outcomes are going to be more likely than others, right? Some things are going to be more certain than others. And probability is the mathematics of uncertainty. These four concepts here form really the basic terminology of probability theory. The concept of a random process, the concept of an outcome of that process, the idea of the sample space of the process, which is just the set of all possible outcomes, and then the idea of a probability model which describes the random process. So let's look at these each in turn. First, a random process, again, is a process with a known range of possible outcomes, but whose actual outcome may not be predictable with certainty. The important thing here is that we need to be able to definitively delineate the set of possible outcomes of the process. An outcome is just a specific end result of the random process. So, for instance, in tossing a coin, an outcome would be either heads or tails, right? In tossing a six-sided die, the outcome would be either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. The sample space just consists of all possible outcomes. So we'll treat that as a set in probability theory. So the sample space is the set of all possible outcomes of a random process. And then finally, the probability model itself consists of the sample space, the set of all possible outcomes, along with an assignment of a probability to all possible events associated with that process. We're going to see that events are basically collections of outcomes. And so we're going to be assigning probabilities to all events associated with the random process. Examples are easy to come by. Tossing a pair of dice and recording the sum, for instance. The outcomes are all possible sums when two six-sided die are tossed. And so that would be the integers from 2 to 12. And this would be a finite probability model because the sample space is a finite set. In a finite probability model, we're going to start pretty much with these because they're particularly simple to handle. We can assign a probability to each outcome, not in any way, because probability assignments have to conform to the axioms of probability, which we'll discuss shortly, but we can assign probabilities in accordance with those axioms. We'll want to do that assignment in a way that makes the probabilities realistic, that reflect the genuine sort of uncertainties that are inherent in the process. And although I'll skip the details for now, the probability assignment for the sum of two dice is given right here. You see the possible outcomes listed in the first row of the table and their probabilities below. And we'll see how this comes about soon, but I just wanted to kind of get this up here as one example of a probability model right here at the beginning. Here's another example of a probability model. This one's a countably infinite model because the sample space is not finite, but it's countably infinite. The random process is to toss a fair coin repeatedly and record the toss number when the first head occurs. So the outcomes here would be that toss number where we got the first head. That could occur on the first toss, or the second toss, or the third toss, or the fourth toss, and so on. So the sample space here would be the set of all positive integers, or the set of natural numbers, right? And again, we would call this a countably infinite probability model because the sample space is not finite, but it is countably infinite. Countably infinite models can be handled in much the same way that finite models are handled. And so we kind of lump these two kinds of models together and we call them discrete. So a discrete probability model is one that's either finite or countably infinite. And we're going to do sort of a deep dive into discrete models first in probability theory. But they're not the only kinds of models. There are models that go beyond that. And here's an example of one of those, a continuous probability model. Suppose we throw a dart at a circular dartboard, radius say 1 meter, and record its distance from the center. Well, in principle, that distance could be measured with arbitrary precision, right? So we're going to go with that. The distance could be any real number. Of course, we're going to assume the dart lands somewhere on the dartboard. So the set of all possible distances would be the set of all possible real numbers between 0 and 1 inclusive, right? So it's the sample space is the closed interval from 0 to 1. This is called a continuous probability model because the sample space is a continuum. It's not countably infinite, right? We know from our work in the foundations of mathematics that the real numbers, or any interval of real numbers, is uncountable. And so this is not a discrete model. Assigning probabilities to a continuous model is a more nuanced thing than a discrete model, and so we're going to postpone that until we have a good understanding of discrete models. We talked about probability models as assigning probabilities to an event. So what's an event exactly? In probability theory, an event is simply a subset of the sample space. So that means it's a collection of outcomes. We can represent that pictorially here with this Venn diagram where the rectangle represents the sample space. So all points inside the rectangle are possible outcomes of the random process. And then an event would simply be some subcollection of those points. So I've got here this oval delineates a certain event. Locations inside that oval would be outcomes that are in the event E. As an example, let's think about tossing a pair of fair dice and recording the value on each die. So you can imagine a first die and a second die, or you could imagine, like, if you're tossing them simultaneously, you would imagine a die, like a red die and a white die or something like that. But we have the outcomes on both that we're recording. So this is a 6x6 table, right? We would, for instance, record the outcome on the first die first, and then the outcome on the second die second. And so the set outcomes are ordered pairs again in this case. An ordered pair ij, where I would be the outcome on the first die and j would be the outcome on the second die. And it makes sense to arrange those in this 6x6 table here. And we see all the possible outcomes of that random process in that table. So let's think about some events. Consider the event that the sum of the dice is 7. I'm going to call that the event A. Event B denotes the two dice being equal. And event C is the event that the first die is 3 more than the second. So we can sort of envision these as subsets of the sample space. There's the event A. As a subset of the sample space, it consists of the outcomes 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. Those are the outcomes, and only those outcomes are in the event A. And you also see A represented as a set of ordered pairs here. The event B, the event that the two die are equal, you see outlined here in green or highlighted in green, and also represented as in set notation as a set of ordered pairs. And then the event C, that the first die is 3 more than the second, is in red here. So events are subsets of the sample space, and often it's very instructive to represent them as such, sort of pictorially. That can help you think your way through a certain problem. Events can be disjoint, which means they have no overlap. In the terms of set theory, that would mean their intersection is the empty set. So we see that events A and B here are disjoint. It's impossible to simultaneously have an outcome where the sum is both 7 and the two die are the same, right? And that's because the sum of any two die that are the same is going to be an even number, and 7's an odd number. So events A and B are disjoint, or mutually exclusive is the word we use in probability theory. The events B and C are also disjoint. It's impossible for the two die to be equal and simultaneously for the first die to be 3 more than the second. But events A and C are overlapping. It is possible to have a sum of 7 and the first die be 3 more than the second. And the intersection is, of course, that outcome 5, 2. So we have this notion, this idea of events occurring. And we say that an event occurs if the actual outcome of the random process is a member of that event. So for instance, if the actual outcome were 5, 2, then we would say, if we actually rolled the die and we came up with first die 5, second die 2, we would say the outcome 5, 2 has occurred. We would also say that a sum of 7 has occurred, right? So the event A would have occurred. And we would also say that the first die was 3 more than the second. So if the outcome 5, 2 occurs here, we see that the events A and C both occurred, but the event B didn't occur because the two die were not equal. And just as a sort of a question in passing that we'll come back to, if we make an assumption that both the die are fair, what would you think would be an appropriate probability assignment for this model? You might want to think about that for a little bit, and we'll come back to it later. Okay, so events are subsets of the sample space. We want to talk about operations on events, and these are going to be equivalent to operations on sets, right? Because events are sets. So we can think about the union of two events. The union of two events is the event consisting of all outcomes that are either in A or in B or in both. So when we say A or B, we mean the inclusive or. It can be in A or B or both. And there you see the event A union B represented as a Venn diagram. We can also think of intersections. The intersection of two sets is the set of all elements that are in common. So the intersection of two events is the set of all outcomes that are in common to both events. And there you see it highlighted on the Venn diagram. You can see that if an outcome in the intersection actually occurs, then both the events A and B would occur, right? Because that outcome would be in both A and B. The set difference consists of all elements in B. The set difference B minus A consists of all elements in B that are not in elements of A, an element of A. So the event B minus A would be all outcomes that are in B but not in A. And you could similarly talk about the set difference A minus B. The complement of an event is the set difference S minus that event. So S minus A is the event that consists of all outcomes that are not in A. And so that's the complement of the set A. And we have an alternative notation for that here as well. A complement just represents that set difference. So A complement is the same as the set difference S minus A. So those are some basic operations on events. We can also talk about relationships between events. And these will mirror, of course, relationships between sets. So we can talk about one event being included in another event. And that's equivalent to one set being included in another set. So we can say that A is a sub-event of B, or that A is included in B, if every outcome in A is also an outcome in B. So you see the Venn diagram here. And, if you want to think about it in terms of outcomes and events occurring, if A is included in B and A occurs, then it has to be the case that B will also occur, right? Because if A occurred, the outcome was in A, but every outcome in A is also in B, so B occurred. The opposite end of that spectrum is mutually exclusive events, and this corresponds to disjoint sets. So we say that events are A and B are mutually exclusive if and only if they have no outcomes in common. And that would mean that the intersection of those two sets is empty. And it would also mean in terms of occurrence, right? If we got mutually exclusive sets, A and B, say, and we know that A occurred, then we know that B didn't occur, right? Because if A occurred, that says the outcome was in A. And if that's the case, the outcome couldn't have been in B because A and B are disjoint. So that's why we use the term mutually exclusive instead of disjoint in probability theory. The idea of mutually exclusive events can be extended to collections of events. So if you have a collection, possibly an infinite collection of events, we say that that whole collection is mutually exclusive if every pair of events in that collection is mutually exclusive. And the Venn diagram would look something like this, where none of the sets in the collection actually have any overlap. So that's a little bit of a discussion of events, and with that, we've set the stage for the axioms of probability. We have enough under our belts, we actually state them now. So this is really ground zero for probability theory. Everything that we discuss further from here will be consequences of these basic axioms. So to set the stage, we have a probability space. That's a non-empty set S, that's our sample space. A collection of subsets of S, and those are our events. And a function, P, that maps that collection of events into the real numbers. We call this function P a probability measure, and keep in mind it's a function that takes as input events, that is subsets of the sample space, and gives as outputs real numbers. So this function has to satisfy the 3 bullet points you see here. Non-negativity means that the probability of any event has to be at least 0. Total unit mass means that the probability of the sample space as a whole has to be 1. And then countable additivity relates to this idea of a mutually exclusive collection of events. It's an axiom of probability theory that if you have a countable collection of mutually exclusive events, then the probability of the union of that collection, that is, the probability that at least one of those events occurs, is equal to the sum of the probabilities of the individual events. That's called the countable additivity axiom. And those 3 are the starting point for probability theory. As I said, everything from here on out will be a logical consequence of those 3 axioms. Much like all of geometry is a consequence of the basic axioms, right, of, say, Euclidean geometry. So what are some basic consequences of the axioms? Well, Theorem 1.1 lists some of the most basic ones. And, these are actually, there's a lot of common sense involved in these. But, again, probability is a mathematical theory. You don't prove a mathematical theorem by saying it's common sense. You prove it by showing how it follows logically from the axiom. So let's take a look at these. The first one, the first bullet point, if A and B are disjoint, then the probability of A union B is the probability of A plus the probability of B. Well, that's really just a special case of our third axiom, countable additivity, right? If you take E1 to be the set A, E2 to be the set B, and E3 on to be the empty set, then that union of all the E's is just A union B, because unioning with the empty set is just doesn't do anything. You get back the same set you started with. And that says that the probability of that union would be the probability, the sum of the probabilities. So if A and B are disjoint, the probability of the union is the sum of the probabilities, and that's just the like n equal 2 case of our countable additivity axiom. Second axiom, the second consequence of theorem 1.1, the probability of the complement of an event is 1 minus the probability of the event itself. We can see, I mean, this is something that would jive with common sense very easily. If I asked the man on the street, hey, somebody told me the probability of rain today was 30%. Can you tell me what the probability it won't rain is? They would kind of look at me strangely and then probably say 70%, right? But that's actually a consequence of these axioms. And you can see that we can do a proof sort of in our heads here. A complement union A is the whole sample space, right? So A complement union A is all of S, because every outcome is either an A or it's not. Moreover, that's a disjoint union. A complement and A are mutually exclusive, right? Because there's nothing that's both in A and not in A. So A complement union A is a disjoint union that equals the whole sample space S. So the probability of A complement union A is the probability of A complement plus the probability of A, and that has to be 1 because A complement union A is the whole sample space, and the total unit mass axiom says that has probability of 1. So that says that probability of A complement plus the probability of A has to be 1, and therefore probability of A complement has to be 1 minus the probability of A. In a similar way, you can prove that the probability of the empty set is 0, and that's because the empty set is the complement of S itself. And then the fourth bullet point actually is kind of a more interesting one, and it leads on to our second theorem. It's talking about the probability of a union of two events when you don't necessarily know that they're disjoint. So for any A and B, disjoint or not, the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And this, again, we can do a proof of, and we will do a proof of this in class, but there's also sort of an intuitive understanding of this part of Theorem 1.1 that you should be aware of, which involves just sort of thinking about what outcomes are being, counted when we take probability of A or the probability of B and so on and add those up. So, probability of A union B means the probability of all the outcomes that are either in A or in B or in both. Now think about that. And then look at the right-hand side of the equation. Probability of A counts all the outcomes that are in A, and that might include some outcomes that are also in B, right? If there's overlap between A and B, then I've counted outcomes in B, some of the outcomes in B, when I compute probability of A, right? Then when I compute probability of B, I've counted those outcomes that are in the intersection twice, once in probability of A and once in probability of B. So probability of A plus probability of B counts outcomes that are in the overlap twice, and that's why you have to subtract off the probability of A intersect B to make sure that outcomes that are in A intersect B are only counted once. And so that's kind of a intuitive understanding of that formula for the probability of the union of two general sets, whether they're disjoint or not, right? If the two sets are disjoint, then A intersect B is the empty set. We know that has probability 0, and so bullet point number 4 there just reduces to bullet point number 1. That last bullet point there actually is the starting point for an important theorem in probability called the principle of inclusion and exclusion. And that's theorem 1.2 here. It basically gives the probability of a finite union of any events. So the first case would be the probability of a union of any two events, and that's just the bullet point we just discussed. And by the way, notice how I've written it here. Probability of A union B is the probability of A plus the probability of B minus probability of AB. It's common practice in probability theory to just suppress the intersection sign. When I want to say A intersect B, I just write AB. I leave off the intersection sign. So that's what we mean here, and we'll be doing that from here on out. But the inclusion-exclusion principle gives similar sorts of formulas for any finite union. So look at the second bullet point. We're talking about a union of three sets, right? The probability of A union B union C turns out to be, what do? You add up the probabilities of the individual sets. So that's probability of A plus probability of B plus probability of C. Then you subtract the probabilities of all the pairwise intersections, all the intersections of two of those sets. So the pairwise intersections are AB, AC, and BC. We have to subtract all those off. That's for the same reason we discussed before. We've counted those guys twice when we added probability of A plus probability of B plus probability of C. So that removes that overcounting of guys in those pairwise intersections. But there's one more thing to consider. What about an outcome that was in the intersection of all three of those events? That got counted 3 times in probability of A plus probability of B plus probability of C, but then it got subtracted 3 times in probability AB minus probability AC minus probability BC. So that's why we have to add that term back in to make sure that probability of outcomes in the intersection of all 3 events are counted. And again, that's sort of an intuitive proof. We'll do an actual proof of this guy in class. But once you get that sort of idea, the remaining parts of the inclusion-exclusion principle kind of begin to make sense. For 4 sets, you add the probabilities of the individual sets, then you subtract the pairwise intersections, then you add back the intersections of 3 sets, and then finally you subtract the intersections of all 4. And so the rest of the inclusion-exclusion principle works in that exact same pattern. Got a few discussion questions that we're going to go over in class. I'd like you to think about these. It's going to be important to talk through some of our examples in the classroom in addition to having these notes. So I'll kind of leave that for your reading. Discussion question here about just describing what the various events would mean in a practical situation. A second set of questions here that basically ask you to use the principle of inclusion and exclusion to find probabilities of certain events given probabilities of other events. And what's the plan going forward? Well, we're going to, as I said before, we're going to study discrete probability spaces first because they're a little bit easier. They're sort of the natural place to start. We'll introduce a lot of key ideas in this discrete setting, like random variables, expected value, independence. We'll also discuss some important classic probability models, like the Bernoulli model and the hypergeometric model, both of which are discrete. And then we'll transition to a discussion of continuous probability models. We'll generalize all those concepts that we saw in the discrete case to the continuous case. We'll explore some important continuous models like the normal distribution, which you've already seen in statistics classes, the Poisson process, which you may not have seen. And we'll talk about continuous and discrete variables in sort of this more general setting. We will then move to a discussion that will ultimately lead to proofs of the fundamental results of probability theory. And those are theorems called laws of large numbers and central limit theorems. And those basically give sort of the sort of philosophical, the law of large numbers in particular gives a philosophical sort of interpretation of probabilities that is justified through these mathematical axioms. And the central limit theorem gives an explanation of why the normal distribution comes up so often in practical applications. So that's sort of the large-scale plan for the class and the semester. Immediately, what is ahead of us is a discussion of discrete processes and discrete models, and in particular, random sampling. So we'll be talking about what does it mean to take a random selection of an individual from a population, what does it mean to take a random sample of a certain size from the population, and so on. This will introduce some more terminology that's common in probability theory, and that will be getting us well on the way to a pretty deep dive into probability theory, which is what this course is all about. So that'll do it for Unit 1. There's going to be some discussion in class associated with these slides and also some homework associated with them. So I urge you to sort of internalize the basic ideas here. They will be with us for the remainder of the semester. And I will see you next time. Y'all take care.